So next up, we have Markku from TII, and he'll be talking about their advancements for virtualization support, both with CAmkES and newly updated microkit from the core platform.
All right, thank you. So we at TII have been working with seL4 virtualization for quite some time now. And last year, my colleague Hannu was talking about how we use QEMU to extend seL4 VirtIO backend support. And this talk is kind of like sequel to that. And we will first do a short recap on what we are actually doing, and then we'll go through what we've been up to for the past few months, and then we'll discuss that what we are currently working on, aside from things we've been working on earlier, and then it's time for reflection. All right. So what we are actually doing is that we are using Linux-based device models to extend seL4 virtualization features. And so basically we've been focusing on VirtIO support, and we are using QEMU as a device model. And we are also developing for Raspberry Pi 4B, and it has its limitations, but it's widely available. We are fully open source, and you can get started from that link. We recently got our paper accepted to TrustCom 2023, and if you want to know more about what we are doing and why we are doing, and want to understand what VirtIO is, I recommend to check last year's talk from Hannu. All right. So let's take a look at what we've been up to for the past few months. So we came up with the kernel module. And that's basically intended to be an API for the Linux-based device models and VMMs. So it simplifies the integration of different VMMs, and also it's intended to abstract the communication with seL4 side. And we are still using CAmkES data boards underneath, and that's about to change. And the change shouldn't be visible to the VMMs at all. The driver itself supports multiple guest VMs, and we also support IO event FD and IRQ-FD, and that's important for the vhost. So what vhost and vhost user is. So basically, it's a mechanism to offload VirtIO word queue processing to an external process. And when we are talking about vhosts, it means that we are actually using a backend as a kernel module. And then we configure that using IOCTLs. And when we are talking about vhost user, then the backend is another user space process, and then we use Unix domain sockets to do the configuration. And typically, the performance is one motivator for using vhost, but for example, vhost user, it also has nice properties of providing some kind of isolation between the backends. And there's also vhost front end, and in our case, it's been QEMU, and that basically handles the VirtIO control plane. So basically, it does the initialization and feature negotiation, and then it passes on the memory region configurations, and then also the word queues, and those are within the region. And then it sends this bunch of file descriptors, and those are the IO event FD and IRQ-FD. And then we have the backend, and that's actually the thing that implements the device. So for example, the vhost net, it basically processes the packages, so sends and receives. And then we have the signaling mechanism. So IO event FD, it basically listens for writes from the guest side. And the IRQFD is the other way around. So when the backend has something for the guest, it will write this file descriptor and it will inject an IRQ on the guest. And here you can see actually the mechanism. So the seL4 Virt driver there, that's actually the thing that provides these IO event FD and RQFD functionality. And the QEMU there is the vhost front end, and that will register these file descriptors there. And then the driver actually listens for when the guest has something, writes to a certain memory location, and if it finds a suitable event FD there, it will then write this file descriptor, and that will notify the backend that, hey, you have something to do. And IRQFD is the other way around. It will write this IRQFD file descriptor, and that's when seL4 Virt driver knows that, okay, I need to send a signal to guest VMM that you need to inject an interrupt. Okay, so we did this with QEMU and Raspberry Pi 4B, and obviously there were some things that had to be done in order to get this working. And the first issue was that the VirtIO PCI expects IRQFD notifications to be MSIs. So MSI is an interrupt mechanism in PCI, and there's also legacy interrupts. So this is kind of the better way for interrupting. And one of the things is that with legacy interrupts, you only have a limited number of interrupts available. And for example, if the device wants to have multiple interrupts, then when it signals the interrupt, then the guest will read that interrupt, and it needs to look for the device for some register that what was actually the reason for this. But when you have MSIs, you can actually have different interrupts for different reasons. And with VirtIO.net, for example, you can assign an MSI for each word queue. Yeah, and there was no support for MSIs in CAmkES Virtual PCI, and also there was no support for MSIs in Interrupt Controller. So what we decided to use temporarily is to use QEMU to provide the virtual PCI and also emulate the GRC v2m device in QEMU. And the GRC v2m is basically an extension for GRC v2, which provides the MSI functionality. And what it does, it basically maps these MSIs to interrupts. And with that, we got throughput of 350 megabits per second. And if you remember last year, we had something like 3 megabits, so it's an improvement, but obviously we can do better still. And as I told you, we are still using CAmkES cross connector, and we know that there are some extra traps involved, so we should be able to improve that. So currently we are obviously improving the communication, and also, as I said, we are temporarily using QEMU virtual PCI. We want to have the support in seL4, and I will tell later why. And also the RQFD abstractions in QEMU were a bit leaky, so we are working on getting the abstractions on better shape. Yeah, and we also did some performance comparisons with with KVM. And so obviously you can see that we are still lagging behind, and we know that we don't get the same performance because we have a service VM is using the pass-through devices. So that basically sets the cap there. But we want to see all of those blue bars go up. So now we also support multiple guest VMs. And the design, it's built in a way that allows us to have multiple sources for VirtIO backends. And also we take assumption that the backends are not part of the VMM. And we actually now are able to mix and match these backends. So something might be provided by QEMU and something might be provided by a native backend. We haven't tested that yet, but it will work. And also, we are using VirtIO PCI as a transport, so backends are PCI devices, virtual PCI devices. So we are still limited to having one service VM serving multiple guests, and there each guest will have its own device model instance. But we are currently working on having support for multiple service VMs. So basically then you can have two service VMs providing different backends. And that is something that we should have quite shortly. And also over time we've been working on microkit support, so we've been abstracting CAmkES away from that. So that is something that we want to get done as well. And also we now are able to trace pretty much everything. So we can get the trace from Linux VMs, and also we can get the trace from seL4 threads, and we are using ftrace formats, and we have flame graphs. Those are cool. Or hot, I don't know. All right, so so also one of the limitations we've had is that the service VM have had access to guest VM's memory, and obviously that's not ideal. So we now can have a build option that you don't want service VM to have access to guest VM's memory. And we used bounce buffers for that, and obviously copying around has a negative impact on performance. But I don't have the numbers, so it shouldn't be too bad. We'll see. All right, so what we are currently working on. So QEMU is quite a big, so it's over 1 million lines of code. And if you only need, let's say, VirtIO net, you don't want to be carrying that around. So we are building these driver VMs without the full-blown device models. And what we are actually doing is that we are building this vhost and vhost user front ends with Rust. And those will be built within the driver VM. And we've, as you probably noticed, that we have pretty much all of the enablers ready. So we are mostly focusing on these front ends. And we see this not as a replacement because there are only so many backends available. So, and why we are doing this? Yes, that over 1 million lines is too much for sometimes, and we want to reduce the device model to what is strictly required. And also we see equally important aspect that we can actually have more collaboration with other hypervisors and other communities. And obviously we are targeting the Rust VMM community. And also there's interesting project called Project Orgo, which is a Linara project. And also it's actually a successor of Project Stratos. And these guys are developing hypervisor agnostic vhost user backends for Rust VMM. And they are also working on having this Rust VMM support for Xen. So we see that as an interesting project. So we are following it closely. And like with QEMU, we actually now, with this, we would have access to production quality VirtIO backends. And equally important, if we want to build something, then we have some place to contribute this new and share the maintenance burden. So how we will do it? We don't want to create another giant application, so we don't want another QEMU. So that's why we are building only dedicated vHost front-end applications, and those will only have certain functionality. We won't be building any new vHost backends. We will focus on getting the front ends done. And it shall support multiple guest VMs, and we will restrict the access to guest VMs memory, and we will use the bounce buffers here. We've been also looking into Kani for some time, and we are planning to use it to verify some of the parts there, but we'll see. And the target is MicroKit, and those are the hardware platforms. So Raspberry Pi 4B and QEMU Virt. And we have started working on this, but this is at early stage, so don't hold your breath. All right, so it's time for reflection. So in our experience, we see this approach of using Linux as quite fairly easy access to high quality and stable device backends. Of course, it comes with a price, but on the other hand, you are actually able to build your product with something. So we don't want people to first start writing drivers. From the very first prototype we had pretty much support for majority of the VirtIO backends out there. And all we had to do was pass through the devices and everything just worked. So it was fairly easy. Also, we haven't seen any blockers for good performance, and we obviously don't compete with the native performance, and that's not the intention here. And also, we thought about this, that you can actually extend this with SDDF drivers if you have native workloads you want to run, but you don't have the drivers there. So again, we don't compete, we want to complement. And this is also something we thought quite a bit. So we've mainly focused on using it as a device model. And we kind of have thought about using it as a VMM. So that would mean that we would transfer some of the responsibilities from seL4 VMM to Linux side. And it has its pros and cons. It would be appealing way to actually do some testing experiments on dynamic behavior. And that's something we've been given thought a bit, but we have come into conclusion that we would do it in a way that native components provide the functionality. So the native components provide the resource management. So typically in other hypervisors, it's the DOM0 or service VM or whatever that will have access to all of the resources, and then it will share this to the guests. We don't think that it should be, in our opinion, it should be done differently. So it can control the resources, but it shouldn't own the resources. Also, when it's used as a VMM, it would be a different role, and also it would need a different API. So the API would be mostly kind of like an extension, because the device model specific stuff would be still the same. So you would have still the same API. But then when it has a different role, it's actually taking kind of initiative. So when you have a device model, it's kind of like waiting that when do I need to serve. And this would bring some more choices to VMMs. So for example, cross-VM would be fairly straightforward to actually get the support there, and also Cloud Hypervisor. I'm not sure about Firecracker because to my understanding it's quite KVM specific, so it might need a little more work. This would probably be usable as a device model as well, but probably you would have to have some hackery there, so maintaining that wouldn't be that nice. All right, thank you.
Question?
Have you looked at using? Okay, hi. Have you looked at using VirtIO-MMU to instead of bounce buffers to restrict the backend VMM or device model's view of guest memory and increase performance in the process?
Yeah, so we thought about that, but we are using the Raspberry Pi 4B, so in it doesn't have IO-MMU. So
No, not a.
sorry.
No, not a real IO-MMU of the system for doing pass-through of real devices, but VirtIO IO-MMU, which allows the VMM to get a view of what subset of guest memory it would need so that you can further scope the VMM or device model backend's view of guest memory and not need to write the whole thing and not need bounce buffers for the inter-VM communication. Like ignoring physical real devices, just increasing performance from VM to VM guest traffic.
We haven't considered that, but thanks for the tip. We will take a look.
So you mentioned there is a bounce buffer. So where is the bounce buffer, in user VM or in the service VM?
The pass-through?
No, the bounce buffer.
Bounce buffer. The guest is actually handling that.
So in the
guest
VM.
Guest is copying, doing the copy to a certain location, and that's how it works. So the service VM that actually doesn't know that it doesn't have access to the guest VM's memory.
Okay, so I assume you start the service VM first, and then you start user VM, right?
Sorry?
So you start the service VM first, then you start user VM.
Yes.
So in that case, if there's no bounce buffer, how do you share the user VM memory to the service VM? Do you need to add actual system core for that one?
Sorry, I didn't quite understand what you meant.
Okay. So you start the service VM first, right?
Yes.
Then you start user VM.
Yeah.
So the service VM need to access the shared memory. When you use the VirtIO, you have to access the user VM memory, right?
We probably should discuss it afterwards. Okay. I didn't understand.
Do you have any plans to document your transition away from CAmkES for the benefit of the rest of the community? Because at some point, others are going to have to follow that path.
Nope. we have Git logs, yeah. But anyway, it's mostly about abstracting CAmkES away. So it's not a much, but of course it's quite a lot of work, and we kind of been thinking that we will, for some time, we will support the both, but we'll see.
This question isn't maybe that relevant or interesting, but I'm curious about it. So I assume most of the overhead from using a driver VM approach, it comes from the unavoidable context switches, but how much have you experimented with configuring the driver Linux kernel to be as tiny as possible and configuring big features out, and to what extent can that reduce overhead? Like, it's kind of a fun challenge configuring Linux to be as small as possible.
We actually haven't tried to optimize pretty much anything. So we've been we've been actually building those vhost related features and just measured the progress there. So the optimization is well now ahead.
So this is an answer for Nick. Our experience showed that the context switches cost almost nothing. They're in the noise, but the VMMs have real performance issues, including the microkit ones, and we haven't drilled down on that. So there's huge overheads that shouldn't be there. But even a copy, in our experience, costs you 5 to 10%, an extra copy.
Yeah.
So that's not going to limit performance much.
Okay, thank you.
Thank you.